afternoon, everybody. My name is Joshua Bailey, Technical Director at Gateway Electronic Components, and we have quite a unique facility in the UK which is dedicated to machining ferrite cores. Not just standard cores off the shelf, but we machine completely bespoke geometries from blocks as well. And the focus of today is really to talk about optimizing designs for machining ferrite, because normally a lot of the designs we see are for prototype runs, so a lot of that design iteration process hasn't happened yet. So the idea is to really ensure that you're designing to be able to machine efficiently and not incurring extra cost on top of your prototype work. And also just to cover some of the background on why we believe machining is actually a viable solution to prototyping solutions. So over the years, before we kind of looked at machining as a viable option for ferrite cores, you would have to talk to one of the large factories in Europe, and you would always be looking at purchasing a pressing and sintering tool, which would maybe cost you, let's say, 10,000 euros roughly, or there would be a minimum order quantity of maybe 10,000, a few 100,000 pieces. And for the newer applications, that's just not really practical anymore. So over the years, especially with introduction of EVs, the chargers, inverters, things like that, we've seen engineers are constantly driving for higher efficiencies, lower costs, smaller footprints, and all of these were normally designed by the engineers, but more recently there's now AI technology out there which will produce some great simulations, all theoretical, and it's about then taking that theoretical work and putting it into application. And the machine shop allows you to do that effectively by, you can order from us for one piece, you could order 100 pieces if you like, but we allow you to then take that theoretical design and apply that in application. You've also got the manufacturers like TDK and Ferrite Cube releasing new materials, and the biggest challenge there is that these materials aren't always available in all of the geometries that you would wish to then simulate your designs in and actually apply them to. And so we can offer a service where some of the new materials that aren't released in that geometry, you can order a block from us and we will machine that same geometry in 3 or 4 different materials. You can again order 1 or 2 pieces in each material, and that allows you to then benchmark each material's performance against each other. And the last point really that we see a lot of now is aerospace and applications like Formula One. They really need tight tolerances that just can't be achieved through the normal pressing and sintering process. And so machining, our tolerances are kind of world-leading tolerances of plus or minus 5 microns. We can hit these tight tolerances with the work we've done in refining our process. Means that these guys are always ordering small quantities, but that makes it super efficient for them because we can hit exactly what they need. There's quite a lot of chat recently on social media around why people shouldn't use custom cores, and that it's expensive or that you have to order large MOQs. And maybe 10 years ago this was the case, not anymore. So this has really been built from the years gone by where you would have to go direct to a factory. Let's say you went to Ferrite Cube direct, say, I need a custom core. But these guys are really, the factories are geared for high volume. They're turning millions of pieces a year out. And for them to have a benefit from that pressing tool and the investment in maintaining that, they really need to see that high MOQ. And we sit in a unique place because we're also we're a part of one of the largest distributors of ferrite products in the UK as well. And so we have a large stock holding that we can pull on from, if you send an order today, we could go and get the stock today. And so we already understand the model where people don't want that high level of commitment in investment in tooling. And so we bridge that gap, and when you come to us, if you need a machine core, there is no tooling costs. Everything is built into that unit price. And so that's exactly why we exist. in the design is key, as I said before. To iterate through those designs and use a pressing tool to do it is expensive, it's long, the lead times are quite long, the MOQs can be quite high. And we really set up to try and attack that end of the market, seeing all of the new applications that exist. And so the next few slides are really designed around, if you're designing a new ferrite core, this is kind of some input and feedback that we've seen and given to customers over the years, mainly to help them reduce their price, but also to understand and get their design ready for pressing. So we don't just focus on actually machining the part, we also look at beyond that, what's your volume expectations, because we understand that if the prototyping design goes well, you then move to your kind of initial volumes, which would probably be machined, but beyond that, you move to an annual volume that would actually be pressed and sintered. But at that point, you have the perfect design, both from a commercial point of view for yourselves, but also from the factory's point of view, in that the design that we present to the factories is ready to be pressed. So we kind of cover a lot of that work along the way. So one of the biggest features we see that always seems to be either overlooked or over-engineered is internal radiuses. And we often see the customers will either heavily define an internal radius of maybe 0.1 millimeters, or sometimes they'll have a sharp 90-degree corner on these internal corners. But that's something that can't be achieved with machining, because the nature of the tools we use dictates that the corner of the tool cannot be 90 degrees. We have to have a surface area for the cutting compound to maintain too, so that as we cut throughout the process, you will see a gradual build-up of tolerance. And so we always ask customers to actually, where possible, define internal radiuses as 0.4 max. We achieve that through standard processes. We can achieve up to 0.2 millimeters max. That tends to add around 20% into the cost, and most customers don't actually need that tight tolerance there. So we say, well, look, if you loosen off that tolerance, then you're going to save money on the unit price. One of the biggest drivers for this at the minute is when you're looking at accommodating your coil in a planar design and using a PCB. Often this gets overlooked, and people will order the PCB first and then look at the ferrite core after, and then realize actually there is a clash in these corners. And you'll see some examples here. So what we suggest is there's two ways to get around this. Our first would be to say, look, rather than us machine this into the ferrite, is actually add a chamfer to your PCB. That's going to be far cheaper, much quicker process. We'll save on cycle time from a ferrite point of view. But often customers have already ordered the PCB, so one solution is to actually add an undercut feature into the ferrite. That removes the clash. It's not ideal, but would then allow you to keep iterating through that design process. One of the other features, again tied to the kind of radiuses of the tools, is we always try and machine the entire product from one operation. So that means we are kind of moving the tool around the product as opposed to moving the product around. That's much cheaper than having multiple setups. That comes with some trade-offs. So in this instance, if we were to machine this in one operation, you would see this radius would become 0.5 mil, because our smallest tool diameter that is available to us is around 1 millimeter. We can decrease that, but to do that, we then have to come in and add another setup to that. So as soon as we move to this, we then have to create specialized jigs. We have to create another setup routine, and in this case, you move from a one setup operation to a three setup operation. And by doing that, we would achieve a much tighter radius in those corners. But again, we would always suggest that if you're looking at those designs, is really widen that gap into these corners to allow us to machine that in one operation. Another feature that we often see over-engineered is break edges. Normally there to ensure that you don't see insulation breakdown, but we see these are normally heavily dimensioned, toleranced features, and they often don't need to be. But again, as soon as you drop in a dimension and add even it's a plus minus 0.1 tolerance, it's a standard tolerance, but you're then adding extra designs in there where you could just opt for a break edge, which would be much simpler for us to run around quickly with a tool. We also advise that, where possible, always specify chamfers. So the reason for that is for us to machine a chamfer, that is one tool in one pass. If you start adding radiuses or fillets into the design, then we have to machine that in around 20 different passes, still one tool, but again, you're building cycle time up. You're adding features that normally are quite aesthetically pleasing, but in reality, there isn't a positive gain to the magnetic performance of that. And that's really the note to take away is if the feature is going to increase the performance of the core magnetically, then we say absolutely dimension it. If not, then move to more generalized terms. Some of the other questions we get asked a lot are minimum wall thicknesses. And this really goes twofold into both machining and pressing. The general rule we say is work to 1 millimeter wall thickness. Smaller can be achieved, but you're then increasing risk of hairline fractures. And we can achieve that, but we achieve a much lower yield normally on these products. And again, when it moves to the factory and you're looking at a pressing and sintered product, you really want to be working in a safe zone. And that 1 millimeter is exactly what that gives you. Minimum hole sizes is something else we get asked a lot. So we specialize in drilling, for especially EMC applications. We see EMC cores with lots of holes in, and minimum hole size we achieve currently is around 0.75 mil in diameter. And one of our key restrictions really is our raw material. So we have blocks in stock from TDK, Ferrite, Ferrite Cube, and Mag Inc. And all of these blocks are available in different sizes depending on whether that's a power material, maybe it's an EMC material. But the ultimate stop for us is the sizes are generally, the largest size we achieve is around 120 mil squared by about 38 mil. We can achieve bigger in normally one dimension, but you're then restricting yourself in another. So another example there is where we can achieve 155 mil by 110 mil. And we always advise that you match the block size to the size of the product. And that's because when these blocks are pressed and sintered, it's exactly like a cake. So you tend to find discrepancies between the pressing density in the middle of the block, between the outer blocks, and that's on these larger blocks. So if you look at specifying a smaller block, then you have a far more homogeneous pressing density and you get better results. Something we can do is actually take these blocks and glue them together for larger assemblies. So we tend to see that in some of the EMC chambers that we do. These can be kind of 30 centimeters in diameter and larger assemblies. And so the only way to achieve that is that this size can't be pressed because the factories just don't have the size presses needed. And so to achieve that, we glue multiple blocks together, or we will part machine, then glue, and then post-process after that. And normally when we glue together, we're seeing a residual air gap of around 0.1 mil. For some, it depends on where that sits, and we normally try and ensure that where that glue line is not going to affect the performance of the core, or we put it in a place where it's going to minimize the risk of its impact. And one of the latest additions to our facility is we've added a furnace which allows us to anneal the machined ferrite. And so that's really important for high frequency designs, because the process of machining can introduce higher losses. And so by annealing this, you reduce that and almost reset the performance of the ferrite back to its original state. And the last thing really is to cover our capabilities. You can come and see us in Hall 7. We stand 128. And we have lots of samples there where you can see some of the work that we do. We cover the kind of large to small. Please come and have a look at that. But in general, we have a motto in the machine shop that is, if you can dream it, we machine it. And we're yet to turn anybody down on that. So if you have a design that you can draw, we will absolutely machine it. But before we do that, we will make sure that the design is refined for that to be economical and a sensible design as a starting point, and to ensure that we're not over-engineering an initial prototype design. So our tolerances I've talked about before, so our AL and inductance values down to plus or minus 1%, dimensional values down to plus or minus 5 microns, and then general machining tolerances of plus or minus 50 microns. Thank you for your time, and please, any questions, please come and see us on our stand.